Okay, so good night or good evening or good afternoon, whatever you are. So let's get working in the URANS case. So in the previous video, we talked about the SAS, the K omega SAS, that force in turn, or the tripping. So now let's take a look at all the other models that we have here. So we have K-Epsilon, the B2F, the SST, Laminar, DNS, Reynolds stress, and Spalart-Allmaras. So before just visiting the folders, we're not going to rerun everything because you have seen that it is expensive, very expensive, time consuming, and we know the solution. Okay, we know what is happening. Hopefully, you have the gist. But basically, we cover everything. RANS, URANS. We're building our way to the scaling resolving. We're missing these two here, but hopefully you have a better understanding now about RANs, URANs. This is an OpenFOAM. I want to stress that the same theory will be with any software. What is going to change is where you do click, okay, how you post-process, but pretty much the theory will be the same. And if the implementation is correct, well, you should get similar values. So, to address something about the closer coefficients. I talked a little bit about this in the theory that sometimes in runs to get that behavior on a steady behavior, you can change, or to get a better matching now with the observation, you can change coefficients now. And here you have these comments, know how you change. So look at that C mu. We know that directly in this formulation that we're looking here of this turbulence model directly will affect the turbulent viscosity. So here you have the effect that will be happen, that will happen. Then maybe on a steady, we saw some cases that you have some diffusion in the wake, in the shear layer. No, so probably changing, readjusting these coefficients can get a better matching with the actual observations. This is tricky, okay? It's not easy to calibrate this coefficient, but it can be done, and it's something that is being done now for URANs to get better results. I don't want to go into too many details to address something about that. So look at here that we have these solutions, the URANs, okay, here SST here with a better mesh, and then we go to scale and resolve it. And look at that, you have the vortex shading here. There is not spacing here. They're all aligned, and here there is more spreading. So this behavior can be corrected with this coefficient. So look at that, you have here more, less, or more mixing, so you can play around to get a better matching. So we have discussed a lot about this, the problem of the URANs and the less light behavior and so on. So be careful about that, and have in mind also that since can be calibrated with coefficient, it is possible. I'm not going to say that will be the solution, but it can be done. So that being said, let's go and study the remaining cases that we have here. Okay, the ones that are missing here is up to you to do as an exercise. It's the same theory. So let's go to Laminar. So remember, Laminar, there is only one option, wall resolving, which will be DNS, no, the Laminar DNS, and in our case it's under resolved because we don't have those superfine meshes. So let me go here and open Fig 3. Usually, as you follow the previous tutorials, steady, if Fig 3, we have friction coefficient, we can use this to validate. So as expected, Laminar will be highly under predict the friction coefficient. You have it here, and very interesting. Look at the matching that you have here with the theoretical viscous law. Okay, but this result is completely wrong. This velocity profile is also wrong. Let me move here, and here we have the movies. You can take a look what is happening. Now this is animation. So look at that. Very interesting that you have here the fluctuations. Okay, so Laminar will have any model, there is no dissipation, you have that, but it's not that much that those fluctuations that you have here to get a good matching, but you have all those fluctuations there, matching here. And question, how long should I run this one? Okay, coming back to that question. So it is up to you, but look at the statistics. So probably you can run, and look at that, this one is still evolving, so you cannot say, okay, I will stop here, because it's still changing in time. also this coefficient. So here we have the blue line, it will be instantaneous, the black one will be the mean value. So you always look at the mean. Probably at this point you might say, yeah, this can be a good moment to stop. So we're talking about 40 seconds, who knows, but you need to monitor, to keep monitoring your solution. So probably it's not the best case to take a look at that, but this is the idea, okay? Statistics are very important. So we'll look at here the laminar, and now let's move to the other extreme and let's talk about K-Epsilon in this model. So the K-Epsilon, remember, is wall modeling, okay? You have some options with the low rate, it's up to you to rerun, but in this case I chose standard K-Epsilon wall modeling, okay? And let's take a look, okay? So remember, K setup is exactly the same, the only difference system time step, and F begins the discretization in time. Okay, so fig 3, okay, this one usually we have the friction. Oh, okay, this is 0. Okay, I need to redo that. I'm quite sure that I will forget that, so that will stay here until the end of time. Okay, so look at that, what we have here. This, okay, and clearly you can see that the K-Epsilon, it is completely averaging, smearing, or erasing those fluctuations. Look at that, this is a very uniform behavior, okay? And now here we have the effect, also different turbulence models, okay? Wall modeling with K-Epsilon and completely smearing now your fluctuations. You don't see anything there. So let me move here, and we have the movie. Let's take at the movie, because this, I think, is what we call is interesting. So look at that, it's evolving here, move in time. It will fit your theoretical value. This velocity profile makes sense. Look at that, even if we are adding here that fluctuation, now you have some oscillation here, but then it will match our known values, reference values here. Probably somewhere in the middle, or 50%, 60% of the flat play. And then here is due to the fluctuation. But look at that fluctuation, we don't see it here. We're missing that entirely due to that averaging process that we have there. Instead, if we run a scale resolving simulations, you're going to see that there. Probably with what we're adding there, it will crash. Well, we need to test that. So this is what we have with the K-Epsilon, okay? Now we move to the next one, and we go to the V2F. So V2F, recall that this one is the one that you are solving, the normal Reynolds stress to the wall, and you have some influence of the wall echo and so on. So it's a good model, but let's see how it behaves for this specific case under unsteady conditions with that source. Now, given that we have seen a few models and we know what is happening. So this one you have it in the two flavors, wall modeling, wall resolving. So let's explore. Versus then here, fig 3. Let me go here, low red, and put it here. Go here, go here. So I know clearly that this is the wall modeling, wall resolving. So as we look at here, pretty much we immediately can see that the B2F, which is a very good model with extra equations. Look at that, it is also smearing, okay, or diffusing that fluctuation. We don't see that fluctuation here. Even though there is a good model, you have extra equations, it has some effects from the Reynolds stresses, models, and so on. It's not capturing that. This is a still image, so let's take a look at an animation to see what happens. Okay, but look at how interesting RSM. So see that at the beginning you have some effect, but then, okay, this is the low rate. Look at that, then everything is diffused, and then you don't have any more the fluctuation. But very interesting, it is that the wall modeling case, it is not adding diffusion here. So this fluctuation, it is still alive there, but then you let it here, okay, and it will be diffused, dissipated, numerical, the match, the time step. But it's very interesting that I will expect entirely the opposite case, that I will have those fluctuations here, and then here everything will be damp, it will disappear, it will be smeared. So this is no strange effect that we have. And well, every different turbulence model, every different node treatment at the wall. And look at that here also, all this diffusion that we're adding, this effect is not seen anymore, and we're matching our theoretical value very well. No, the low rate instead this one. There are some differences, probably you let it run, you will get good matching, but there you go, okay? So the B2F, that is a model that I really like. It does not behave very well in this case. So the K omega source, we already studied this model. So in this one, the no source, we don't have that. We know what is happening. And by the way, all these cases, if you disable the source there, everything will be, you're going to get your standard steady solution. So let's go to the K omega SST. So remember that the SAS is based in this, and then you have that extra source terms, and then you will add those extra behaviors and coefficients and so on. So let me go here, and K omega SST, we know that we have it in two flavors, high, low, re. Also remember K omega SST, you have the wall distance and so on, so we have covered that, but just to remind you. But the K zeta exactly same as what we have done in a steady, okay? When it comes to boundary conditions, remember then you need to adjust your system directory for the numerics. So let's go here, as usual, let me open 3, let me go low re, pattern view, put it here, move it here, boom, there, and there you go. So by looking at these two still images, I already know that the low re kind of is conserving you have is not dissipating those fluctuations. This one kind of probably you have something that is still alive here, but then everything is dissipated here in the wall modeling. Okay, so kind of opposite to some other cases that you have the opposite behavior. In this case, you have what I will expect now that the finer mesh will keep those fluctuations alive. So we have the study image. Let's move to the, okay, let me go here, and here we have, okay, the fluctuations. So look at that in this case, now the fluctuations are being damped or smooth or raised from the solution here. We have same scale, well, a little bit smaller here. Okay, so we move and let's take a look at the animation. And this is it. Okay, wall modeling, wall resolving, and pretty much look at very interesting these results. Now the K omega SST, look at that, it's not dissipating the behavior. You have it there, you have your torrent viscosity, all the fluctuations, everything you see here. The wall modeling, this is what I was expecting, contrary to the other case. That now here you are going to see those fluctuations, but now here everything will be damp or erased or diffused from your solution. You don't see any fluctuation here, very small. Instead here, look at that, this is still dancing. Okay, so this is our K omega SST. Now another reason to say now that the K omega family of turbulence models is the most reliable one. Now, we have seen many of them, but consistently you will see that K omega family of models, they will give you, physically realistic results, and it will behave according to the physics that you are expecting. But okay, this is a kind of a synthetic case, so we don't know what should happen, but for what we have studied, we know that this should be the behavior. Okay, so K omega SST, another one down here. Okay, so feel free to rerun this one. Remember, this is time consuming. The question, how long should I run? Well, you have it there. You look at your statistic, and it will be up to you to choose when to stop the simulation. And remember, this will generate a large amount of data. Okay, so be careful to deal with large amount of data. And then let's go to the Spalart-Allmaras just to end this discussion. So Spalart-Allmaras, we have the both flavors, high, re, low, re. Let me open the figures here. Let me go to this one, and let me go to this one. Wasn't there, so it's not there. There you go. So we compare both here, Spalart-Allmaras wall modeling, wall resolving, as from the other cases, both of them are dissipating, not the fluctuations. We don't see the fluctuations. Maybe at the end here, we'll kind of try to match now the theoretical results, but yeah, well, we have that behavior now. This synthetic result will introduce that source there to make it unsteady. But as you can see, this makes completely sense. Now let me check here, okay, and let me go to the movies. So play and play and play here. Go. So look at that, the wall resolving at the beginning. And again, we go to the opposite case, to the K omega SST. So in the K omega SST, the low ray was resolving that fluctuation. In this case, it is the opposite. So I would expect the low ray just to resolve everything, not to diffuse everything. So we're losing the fluctuation. Instead, look at that, the wall resolving here, the wall modeling, sorry, okay, you still capture that fluctuation there, and you see it here in your friction coefficient or signal. And well, another strange behavior, okay, so this doesn't mean that the Spalart-Allmaras is wrong, K omega is wrong, depends now what is happening. The mesh, numerics, coefficients, many variables are coming into play. And well, to revisit again the question, when should I stop the solution? Just look at your statistics. So look at what is happening here. So you start and look at instantaneous, and the black line represents that mean value. And look at that, it's still changing. So I cannot say that I can stop here because it is changing my mean. Also my mean here, it is changing in time. So you should monitor. In this case, we have monitors here, but it can be anything. Usually the best monitor is forces, but not always you are monitoring forces. Can be any quantity. And see here that maybe at this point, at 40 seconds, maybe you have both of them matching, they are not changing, or in particular, the mean value is not changing anymore. So maybe this can be a good moment to stop your simulation. Who knows? There are no more fluctuations here, okay? Who knows? Okay, but it's up to you, and you need to monitor that. So that's why this is also, the post-processing is very, very time consuming. I like to compare it with overset meshes for those that knows what overset meshes are, and if you have worked with overset meshes, that is a hell to post-process those simulations. Same with unsteady. So imagine overset but plus unsteady is a hell. Too much data, a lot of statistics, things to monitor, and sometimes you cannot get an idea of what is happening by having that data, and you need to keep running and running and running. So this is it, okay? And well, let me close. Hopefully we have a better idea. And let me go back here to the KCST now, just to mention about and open this one. About the statistic, know when to stop the simulation. And look at that. The black line still is changing. So this is not a good instant to stop, because it's changing. You let it run, and look at that, it keeps running, and this is the issue. Now get those statistics. So advice, never forget to compute your statistic in your simulation. So see here that I have a statistic for friction coefficient. That quantity exists, that quantity, I'm getting that value. And probably here already, maybe you can say at 60 seconds it's not changing anymore, but probably here, let's go to 30. Maybe you had the false impression that this was okay. But look at when you evolve and you move to another instance, see that it is changing. And it still is changing from 60 to 70. And that's why this case actually runs to 100, because I run many situations, I compute many variations, I compute a statistic. I know that something about 90 already you have it. Okay, it's not changing anymore. I also check invariance, standard deviation, and so on, and around 90 for all cases is already okay, but I let it run to 100. I like round numbers, and that's it. Okay, so this is Spalart-Allmaras wall resolving, and look at that. It's not dissipating, okay, any energy there. and to stress this and to bring it back. And what was one of the cases, Spalart-Allmaras. Okay, I forgot the Reynolds stress actually. Yeah, I need to address that one. And you put this one and look at that, this one, you let it run and then it's dissipating. So I would expect something like the K omega SST, but it's happening here, that situation, but nothing, you shouldn't be afraid of that. Okay, so finally, let's talk about this one. Reynolds stress, the LRR. This is the formulation I like. This one, remember, you only have it in the flavor of HRE. And this is very interesting model. Okay, as I say, these are extremely difficult to make conversion, steady or unsteady. Very difficult. And actually, I think I didn't manage to get these models to 100. They were for some reason always crashing, and I didn't want to spend too much time trying to get to stabilize. So in ParaView, let me go here. So uniform is starting from uniform conditions. Init starting from another URANS solution. I don't recall which one I use. So it doesn't matter what you use, you will get pretty much the same. Let me open init and let's take a look. And actually we can compare both. So init, let me go ParaView uniform 3. So both of them are world modeling. Remember that the Reynolds stress in OpenFOAM are world modeling. And you have here, this was the initialization. This one it is from the uniform one. So in theory, the one using initialization should convert fast because you don't have that initial transient. Okay, so remember, you start from 0, you have an initial transient. So you are saving that, okay? So you can get an steady simulation very fast, some colors fast, and then save that initial transient. And okay, so let me move there. But both cases, as you can see, they are dissipating the fluctuation. We don't see the fluctuations here, okay? And there you go. We have Reynolds stresses that I need to comment something on the animations here, and then run the case just to show you something. Play, and look at what we have here. And there you go. Immediately the Reynolds stresses are dissipating, everything is mirroring all the fluctuations. Now, I will say presumably this is due to the effect of the wall echo. Okay? Requires some study, but look at very interesting. You dissipate, and at one point, and also in this case, boom, you have again the onset of the instability. This is what I'm talking about, that you need to add, in some cases, you will already have here that forcing, but in some cases you need to add that energy to avoid the dissipation of the turbulent kinetic energy or whatever quantity. And look at that here, you have it. Everything start to go crazy here. In this case, this one arrived stopped at 70, but I recall that both situations they crash about 75 or 80. It's very difficult to get conversion. But what is interesting, and actually here, and let me put here and let me move. Now we have the same video. Is that if you look here, you will see that we have average quantity, instantaneous quantities. Here we have Reynolds stresses computed by the Reynolds stress model. So you have your quantities, but from the statistic, you can get that. And let me clarify that. Okay, so let me close that. Hopefully everything's clear for you here. And let me do something. Let me go Reynolds stress model. Let me go here. Let me run there. I just want the mesh. I will stop it immediately. Attention. In the cases here, you have the log files. So already run the case. So if you want to plot everything and look the timings, so you got that information there. But in solutions, you have the solutions. So you can get one solution here. It's up to you. We'll get the init. And let me go 6. Let me get 60. Okay. I don't want to run everything. Okay, it's not very time consuming. And let's do the post processing. Apply, and there you go. So you have time 60, you have your velocity, everything, and look at that, you have your Reynolds stresses. No, this is the the production term, and like computing also statistics. So you have the mean value, everything, your Reynolds stresses, and you have all the components here. Okay. Very interesting that this model. So recall that. Let me rotate. Let me put the mesh. It's a 2D mesh. Remember that this case is 2D. For some reason, this case, this model, it is computing in set. Look at that, set is this one. We shouldn't have anything in set because it's 2D. And look at that, you have this. So a source of error, since that you need to monitor, be careful, okay, about that. So this is very strange. I don't recall. I think somewhere have an explanation to this, what is happening. It might be a bug, it might not. Okay, but okay, be careful about that. And some of the reason why this case crashes because you have this component that is now you're getting something there. So you need to add some kind of force in there to avoid that, and it will work. But many times it crashes in 2D cases because of this behavior. It doesn't mean that in 3D will run. In 3D also crash, but they're very, 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 very difficult to make conversion. So this is just to take a look at that. But what I want to open here is an state. You have different states, and for what we call should be 5. State 5, the one that I compute Reynolds stresses, and we have some quantities there, and there you go. Yeah, this is the one I wanted. So we have here your Reynolds stress, XX, this one, so the most energetic one. Then you have XY, the shear one, the one responsible for the mixing. Here we have the fluctuation prime, so we don't see anything there. U prime, but it doesn't matter. Interested here. So if we look at here, this plot, look at that. Here we have quantity of interest 1, 2, but we have average from OpenFOAM and average in ParaView. That is, let me explain you. In OpenFOAM, every single iteration you are computing in the statistic. In ParaView, you will compute the same statistic, but with the time set that you save. So if you save time set 1, 2, 3, 4, you will use those time steps to compute the statistic. OpenFOAM will be more accurate because you are getting the time step 0001, 002, 2, 3, and you will have more statistics. So if you want to get the same value, you will need to save an incredible amount of data. Just to point out that. But what is interesting here that to show you how to compute Reynolds stresses, let me go here and here. So you have the traditional calculator. This is the new one that we add U prime. So U prime remembers the fluctuation. Instantaneous value minus the mean. The mean coming from OpenFOAM. And you get your fluctuation. And remember the definition of your Reynolds stress. Let me see if I have it somewhere here. I don't want to open any. No. So let me go here. It should be here. And this is it. So these are your Reynolds stresses, and this is what you have. The average of the product of the fluctuation. Be careful of the definition that there are this can be very different things. Okay, this is different from the product of the average of the fluctuations. Okay, that is average on this times average on this. Okay, they are very different things. So you need to compute this one. Okay, so we'll compute this quantity in OpenFOAM U prime, you multiply, and then when you have this product, you average that product. Okay. So this stuff here, this is U prime that you see in the OpenFOAM dictionary, and let me open that dictionary. It's in here. When you have the statistic, that quantity there is this prime to mean. Okay, prime to mean. It is basically this quantity, no? So it will be for whatever quantity, pressure, velocity, and so on. Okay, so that's why you use velocity as the Reynolds stress. So look at that. We're looking here. So you compute your U prime, you move here, U prime square. So look at that. You compute that product. Okay. This product, still you have an average. And now the next, it is temporary statistic. So here it is in Paraview, you get your statistic and you plot here. So you will see a difference between the one computed in OpenFOAM and Paraview, because I don't have enough data in Paraview to get that. But that will apply precisely for the quantity of interest one, which is the Reynolds stress. For the velocity, it happens that you get a good matching here. Okay. So this is how you can compute, and hopefully you get the idea how you can compute the Reynolds stress. And you will do the same stuff now with xx, xy, you get all your prime, get the product, and after you have the product, you will do the average of the quantity. When you enable this, OpenFOAM is computing all those statistics. So by every means, use the statistic of OpenFOAM. If you want to get the statistic in Paraview, you will need to save a lot of data, okay? But it works in the same way. So I think later we're going to do some videos using DNS data, and we're going to see how to do all this stuff and compute all Reynolds stresses and get the budget, but we're going to have a lot of data available, so that's why we will be able to do it. Then here, okay, so this is to show you. Here you have your Reynolds stresses, so you have all the components, xx, xy, xz, and so on. And look at that, you have a contribution in set that you shouldn't have because it's too deep, but still you have it. And you have it in function of y plus and in function of the distance from the wall. Okay, so pretty much, okay, at this point we cover all the unsteady case, the URANS, and hopefully now you have a better idea. So to end this, I want to stress something in URANS is the myth, okay, and let me go here, of having no URANS solution with less like behavior. That doesn't happen very often, so do not expect to get this with an URANS model, okay? Do not expect this. If you want to get this, you should move to scale resolving. If you get something like this with URANS, be careful. No, you be a little bit suspicious about those results. Okay, so URANS, you don't have any dependence on the grid. Okay, we also saw that in the SAS in the papers, and it's written there. But this is something that you are going to see only in scale resolvents. In URANS, you don't have this. And to end here, I always like this image. So I think this is something that a tutorial we need to do so you get an idea. And this is what you're going to see with an URANS. Okay, this behavior, you're going to resolve very well the average quantities, but this breakup, this vortex stretching, this stuff, it's very difficult to capture in URANS. Doesn't mean that your solution is wrong. We have seen why that happens, that we know that, okay, that is due to that averaging among many things. The main reason, one of the main reasons will be the averaging. Also look at here, the spacing between the vortices. There is less diffusion spreading in the wake here than here. Okay, so with this, I'm done. Thank you very much for your attention and see you next time. Bye.